Welcome to The Explainer. Today we're unpacking a fascinating and, let's be real, highly controversial critique of modern science. It comes from physicist Sabine Hosseinfielder, drawn directly from her book, Lost in Math: How Beauty Leads Physics Astray. Her central and honestly pretty alarming thesis, theoretical physics, is stalling. And it's not because we lack the mathematical tools. It's because scientists are actively prioritizing beautiful math over hard empirical evidence. Okay, let's dive into this. For decades now, the quest for fundamentally new laws of nature has seemingly hit a brick wall. So we really have to ask ourselves, why hasn't theoretical physics seen any major experimental breakthroughs in cosmology or particle physics in over 40 years? Have we just reached the limits of human understanding? Or is there a fundamental flaw in how modern physicists are choosing their hypotheses? Well, the answer, according to our source material, lies in a severe structural crisis. You see, for years, the high-energy physics community promised us that building larger, infinitely more expensive accelerators would inevitably uncover a whole suite of new particles beyond our current standard model. I mean, billions of dollars were spent building the Large Hadron Collider. But the results? Genuinely shocking. With the sole exception of the Higgs boson, the LHC detected 0 new particles. Null results. And this massive failure has pushed a whole generation of physicists to basically invent untestable laws, just to keep their beautiful models alive. So here's our roadmap for today's explainer. We're going to cover the crisis in physics, the trap of beauty, when beautiful theories fail, the fine-tuning problem, and finally, escaping reality into the multiverse. All right, let's jump right into section 1, the crisis in physics, the broken compass of theoretical physics. We are seeing a major shift in modern research. The field is moving away from uncovering observational truths and moving towards formulating breathtaking equations purely based on concepts like elegance and symmetry. Now, what's really interesting about this mindset is how perfectly it's captured by legendary physicist Paul Dirac. He explicitly stated that mathematical beauty is actually more important than empirical data. To modern critics, this is a flagrant violation of the core scientific principle of absolute objectivity. I mean, think about it. Why on earth should the fundamental laws of nature care about what the human brain perceives as aesthetically pleasing? Moving on to Section 2, the trap of beauty, cognitive bias in fundamental research. That belief that Dirac held, it hasn't gone away at all. In fact, it's become a deeply entrenched cognitive bias in fundamental research, blindly passed down from academic advisors to students as this kind of untouchable professional intuition. So, what exactly do physicists mean when they call a theory beautiful? Well, it usually comes down to 3 main criteria. First up, simplicity, seeking to reduce the number of assumptions. But the methodological risk here is pretty obvious, right? Nature might actually just be structurally complex. Then there's naturalness. This is the absence of unexplained, awkwardly large or small numbers. But relying on that biases us toward a uniform distribution hypothesis. And finally, elegance, looking for a sudden, surprising mathematical connection. That is an entirely subjective criterion heavily influenced by academic culture. The whole point of science was to overcome flawed human intuition, yet physicists are out here defending untested hypotheses using these exact subjective aesthetic criteria. Which brings us to Section 3, when beautiful theories fail, historical precedents. If we look back at the history of science, it is incredibly easy to prove that this isn't the first time beautiful ideas have completely blinded brilliant minds to the messy reality of the universe. Take Johannes Kepler. He initially thought the solar system was built on perfect Platonic solids because, hey, it was mathematically beautiful. Meanwhile, Galileo stubbornly insisted orbits must be perfect circles. They were both wrong. Real orbits are messy ellipses. Later on, Fred Hoyle flat out rejected the Big Bang because he found a definitive beginning of time to be a really ugly concept. He favored a beautiful, eternal, steady-state universe, which was later entirely refuted by cosmic microwave background data. And in the 19th century, Lord Kelvin and Maxwell absolutely loved the quote-unquote inevitably true vortex theory of atoms. That was completely destroyed once we discovered the chaotic reality of microscopic quantum mechanics. That leads us straight into Section 4, the fine-tuning problem, the messy reality of the Standard Model. Today, physicists heavily rely on the Standard Model, which utilizes something called the separation of scales. Think of a calcium atom in your bone. Deep inside its nucleus, absolute quantum chaos reigns. But on the outside, it behaves totally stably. The large scale just doesn't care about the tiny details. However, mathematically speaking, the standard model is incredibly ugly to theorists. For one, it entirely excludes gravity. Plus, it requires 25 free constants, like particle masses, to be entered manually from experiments, rather than being neatly predicted by the math itself. But the ugliest part of all, the number 14. This relates to the Higgs boson. Because of intense quantum fluctuations, the theoretical mass of the Higgs should actually be enormous. To make the math match the incredibly small mass we actually observe in reality, physicists have to introduce an absurdly precise mathematical subtraction. They are manually canceling out massive numbers to an accuracy of 14 decimal places. To theoretical physicists, this massive fine-tuning is a fatal aesthetic flaw. It totally lacks that naturalness we discussed earlier. So, to fix this glaring mathematical ugliness, theorists championed supersymmetry, or SUSY for short. The idea was elegantly simple. Just propose a hidden superpartner for every known particle. Those partners would mathematically cancel out the quantum fluctuations automatically. Poof, no more ugly 14 decimal fine-tuning. The Large Hadron Collider was fully expected to find these superpartners, but it didn't. Finding absolutely nothing means nature simply isn't natural by our human standards. As renowned physicist Nima Arkani-Hamed noted with clear frustration, the field is now facing a harsh cognitive reckoning. And finally, Section 5, Escaping Reality, the Multiverse, and the Retreat into Metaphysics. Instead of admitting that their aesthetic criteria might just be wrong, many theoretical physicists are choosing to double down. Rather than correcting the math to fit reality, they're inventing completely untestable new realities. The ultimate example of this is the cosmological constant, which drives the expansion of our universe. It is a staggering 120 orders of magnitude smaller than what quantum field theory predicts. Talk about incredibly fine-tuned. Since they can't find a beautiful mathematical reason for this, many physicists have turned to the anthropic principle and the multiverse. They argue that there are infinite universes with different random laws, and we just happen to live in the one where the laws allow stars, planets, and conscious humans to form. But opponents like George Ellis and Paul Steinhardt argue this is a total disaster. They call it the complete destruction of empirical science, because at the end of the day, you simply cannot test or falsify a multiverse. To justify these wild theories, Nobel laureate Steven Weinberg used a brilliantly simple cosmic poker analogy. He argued that if a poker player gets a royal flush 3 times in a row, you're going to suspect a cheating dealer, meaning you seek a deep, hidden mechanism. But if they get 3 completely random, messy hands, you don't ask why, because random things happen all the time. Weinberg is basically arguing that the messy, fine-tuned constants of our universe are just random hands dealt from the infinite deck of the multiverse. But Sabine Hosseinfielder pushes back hard against Weinberg's logic with this absolutely vital question. What if we only ever get to hold one hand? We don't actually have a probability distribution for the laws of nature. We only have one single universe to observe. Claiming that our universe is somehow rare or unnatural requires assuming a massive, unprovable mechanism churning out other universes. It's an overly complex metaphysical escape hatch, designed purely to avoid admitting that our current equations are deficient. And for the future of the scientific method, that is a very dangerous precedent. And look, this demand for aesthetic beauty isn't just happening out in cosmology. It's polluting the foundations of quantum mechanics too. Quantum math gives us incredible precision, yet it relies on unobservable wave functions that magically and instantaneously collapse when they are measured. Physicist Anton Zeilinger actually proved this bizarre non-local behavior across 144 kilometers in the Canary Islands. Einstein famously hated this, calling it spooky action at a distance. It is aesthetically repulsive to a lot of scientists because it suggests that human measurement dictates reality itself. To deal with this ugly wave function collapse, the field is deeply split. On one side, you have the minimalist Copenhagen interpretation, whose blunt, unofficial motto is basically, shut up and calculate. It's highly pragmatic, sure, but it completely avoids structural reality. Then, in stark contrast, you have the many-worlds interpretation, which argues the wave function never actually collapses. Instead, the universe infinitely splits into parallel realities every single time a particle moves. As expert Chad Orzel points out, because the math works, researchers are completely overlooking deep structural ambiguity. They're forced to choose between harsh pragmaticism or structurally absurd mathematical beauty. All of this leaves us with one crucial defining question. Will theoretical physics return to reality or remain entirely lost in math? As we've seen today, the universe clearly does not care about what humans find aesthetically pleasing. Simplicity, naturalness, and elegance, these are cognitive biases, not cosmic laws. If the field of theoretical physics actually wants to move forward, it may have to abandon its beautiful equations and finally embrace the ugly, messy, yet incredibly fascinating reality of experimental data. So, what do you think? Thank you so much for joining me for this explainer. I really hope this leaves you questioning the hidden rules and assumptions behind the science we take for granted every day.